It is, yes. Thank you. Can you, I've shared the wrong screen here, haven't I? Let's see. So, uh, I hope you can see my screen and hear me okay. Good. Well, it's a great pleasure to have the opportunity to come and speak to you this morning. So, what I'm going to talk about today is some of the work in my group, focusing on using low temperature topochemical reactions to make unusual solids. So one of the interests in the research group is making solids that have physical behaviors a bit like the two compounds we can see here. So the one on the left should be familiar to most people. So this is yttrium barium copper oxide. So this is the first example of a high temperature superconductor with a superconducting transition above the temperature of the boiling point of liquid nitrogen. And on the right here, we have lanthanum calcium manganate, which is an example of a material that has a large magnetoresistive ratio. So it has a large change in its electrical conductivity as a function of applied magnetic field. And the thing that these two compounds have in common is that their physical properties derive from the d electrons in the orbitals of the transition metals, so copper in this case and manganese over here. But we can't understand their physical properties on the basis of just the electrons on a single atom. What we realize is their properties are a collective feature of the d electrons on multiple transition metal centers acting as a group. And so we call these materials sort of correlated collective behavior materials. And so from a chemistry point of view, and after all, I am a chemist, I'm interested in making things, we might ask ourselves, well, how would we go about making new solid state compounds that exhibit similarly complex electronic behavior? How are we going to do this? Well, one way we could think about this is to consider a transition metal oxide system, and we are going to mainly focus on oxides. We could consider such a system as really a set of coordination polyhedra. So we could think about the local coordinations around particular metals and realize that this solid could be made up by fusing multiple coordination geometries together. And so we could think about building up lots of possible structures or lots of possible compounds by thinking about choosing a transition element from the list, or maybe even two. And then we could choose the oxidation state for the transition metal. So we set the number of d electrons each one has. And then we could think about their local coordinations to define their local electronic state. And then we could think about fusing them into a three-dimensional structure. And then we could come up with a huge list of possible combinations if we compare all the combinations that we could have of the element, the oxidation state, the coordination, and the structure. And would have a vast library of compounds that we could go after. And so the logical thing might be to try and make all of the compounds in that library. And as soon as we try and do that, we realize we run into a problem. And the problem is to do with solid state synthesis. So if we consider a simple synthesis of a ternary oxide, so two metals and oxygen. So we take this lanthanum iron oxide example, we could consider making this compound from the simple combination of the binary oxide, so lanthanum oxide and iron oxide. And so what I can do is take the two powders and mix them together. And what I see is that nothing happens. I just have a mixture of the two powders. I need to heat the system to at least 800 degrees C to get a reaction, and more reasonably 1000 degrees C to get a reaction at a reasonable rate. And the reason for that is that I need my ions in my separate particles, maybe this orange one's iron oxide and the grey one's lanthanum oxide. I need the particles to diffuse, the ions to diffuse between the particles to make the ternary phase. And what we find is that the barriers to diffusion in the solid state, particularly for oxides, are very high. And in fact, what we can see is that these barriers to diffusion, what we call the mass transport contributions, contribute at least 90% of the activation energy in solid-solid reactions of oxides. And what that means is we could have an energy reaction diagram that looks a little bit like this. So I'm plotting the free energy of the system vertically, and then the reaction progress horizontally. And so what we could see is our starting materials have this energy here. We have lanthanum oxide and iron oxide, and we can think about them reacting to make two different forms of LaFeO3, form number 1 and form number 2. And we can see form number 1 is more thermodynamically stable than form number 2. However, what we can also see is the activation energy to form these two compounds is basically the same, because it's dominated by this large diffusion barrier contribution. And this presents us with a problem, because if I supply enough energy to make form number 2 to get over this barrier, I've also given the system enough energy to get over this barrier. And so what we find is when we heat the system up, the two products enter a thermodynamic equilibrium, and actually an equilibrium with all the other possible products. And what we find is we make the most stable phase or combination of phases. And so under these conditions, we really can't make metastable phases here. So of that big combinatorial array of possible compounds we were thinking about earlier, I'm only going to be able to make a small subset of them by this route, because I can only make the thermodynamically most stable ones. And unfortunately, the situation is even worse than that, because if the products of these reactions are thermodynamically controlled, so if their thermodynamic stability is the key feature, what we'll find is that they'll be made up of the same building blocks, because thermodynamically there are preferred coordination geometries for our transition metals, there are preferred oxidation states, and preferred structural frameworks. And so what we find is for any one composition, I can only make one thing, the most stable compound, the most stable phase. And unfortunately, the stable phases I can make all look quite similar. So this is a bit of a problem in solid state synthesis. So how can I think about getting around this? Well, one thing I could try and do is I could try and change the relative stabilities of my competing phases. Now that's extremely difficult to do. So you could try and change the relative stability of our product phases by changing pressure or maybe changing temperature, but that's really challenging. A better way of approaching this, or a simpler way, is to realize what I want to do is actually change the activation energies. And this is what we do in chemistry all the time. We think about molecular chemistry. Reactions in molecular chemistry are performed under kinetic control. We make the product that forms the fastest, not the one that's necessarily the most stable. And so what we want to do in the solid state is try and change these activation barriers so that they're different. So how might we do that? Well, we can get some clues from existing chemistry. And a good example is the lithium-ion battery. So this lithium cobalt oxide should be familiar to most people. Actually, it was first used in a lithium-ion battery here in Oxford, actually, about 10 meters from where I'm currently sat. John Goodenough used this for the first time in a lithium-ion battery system. And what you can see in this system is if I apply an oxidant, or if I do this electrochemically, I can extract lithium from the lithium cobalt oxide framework without changing the rest of the compound. And the reason I can deintercalate lithium from lithium cobalt oxide is that the lithium ions are much more mobile in the framework than the cobalt or oxide ions are. And what this means then is that the activation barrier to turn LiCOO2 into Li1-X COO2 is much lower than the barrier to form the thermodynamic products, which are a decomposition reaction to cobalt oxide and lithium chloride. And so we can use this idea of the different mobility of the ions leading to different reactivity of the ions to think about making metastable materials. And actually in the lithium ion battery research area, most of the challenges actually arise from controlling the size of these activation barriers so that we can choose to go over this one selectively rather than a variety of different decomposition products. Okay, so what we find actually in many transition metal oxides is that the oxide ions are the most mobile species, much more mobile than the metals. And so what we can do is follow a two-step synthesis strategy. Step number one, we can do a conventional thermodynamic high temperature synthesis. So in this example, I can take titanium oxide and I can take yttria and grind them together and then heat them at a really high temperature to make this phase here, Y2Ti2O7, which has the pyroclore structure. So this is just a thermodynamically stable material. But it's what I do next that's interesting. What I can do now is treat these with a reagent, and I'll talk about these hydrides in just a second. And now I can exploit the higher mobility of the oxide ions in this framework than the metals to extract oxygen from the system and make a reduced compound, so Y2Ti2O 5.9. And this is a metastable titanium 3+ compound that I can't make directly by combining any combination of titanium and yttrium oxides. And we know that this is a metastable phase because the thermodynamically stable phase with the same composition has the perovskite structure. So by adopting this two-step strategy, where in the second step we use the higher mobility of the oxide ions, we can make highly metastable materials. Now the reagents we use are binary metal hydrides, and these are really good at extracting oxygen from complex oxides at low temperature. So we have really three reagents we use commonly. So the first is sodium hydride. This extracts oxygen from a system to make sodium hydroxide. So a good example is LaNiO3 goes to LaNiO2, and we'll have a look at this reaction in just a moment. And now we see that the hydride ion is a 2-electron reducing agent. It goes from H- to H+. And this is a very versatile reagent. But the problem we have is that sodium hydride enters an equilibrium with sodium and hydrogen just about 250 degrees C. And so this is the highest temperature we can do these reactions at. Alternatively, though, we can use lithium hydride. So lithium hydride is a 1-electron reducing agent. It extracts oxygen to make lithium oxide and hydrogen gas, so H- to H0. And here's an example of an iron 3 to square planar iron 2 compound. And now we can get the temperature a little bit higher. So now we can get to about 550 degrees C before lithium hydride becomes lithium and hydrogen. Although we need to watch out for the lithium insertion reactions that lithium hydride can do. And the third and probably most versatile of the hydride reagents is calcium hydride. So calcium hydride extracts oxygen by making calcium oxide and hydrogen. And here's the example we've already seen. And now calcium hydride is stable up to about 850 degrees C. So we can really explore extracting some rather immobile oxide ions from our complex oxides. And by using these reagents, we can make a whole selection of extremely unusual transition metal oxides, where we have the transition metals in really unusual oxidation states. So here's some nickel 1, but we can have examples of manganese 1. Here's ruthenium 2 with some nickel 1, or we can have iridium 2, or we can even make compounds in which the cobalt oxidation state disproportionates, which we'll talk about in a minute. But rather than, well, and what we can see actually is that the compounds themselves have interesting physical properties. I'm actually going to focus on this one here. This is actually the material where it all started making this compound. And you can see this was done quite a long time ago, 1999. But 20 years afterwards, a group in California run by Harold Wang basically took this chemistry and put it onto a thin film. And what they discovered, and it had been widely predicted for quite a long time, But what they discovered, if you put this material on a thin film, you can make a superconducting compound. It's Nd.8Sr.2 NiO2 that you make from the reduction of the equivalent O3 compound. And so it was quite nice that 20 years after we explored the chemistry, someone actually used it to make this superconducting material. And now there are a whole series of materials in this series, which is quite a hot research area. So what I could have done is in the talk is show you a series of exotic materials and talk about their physical properties. But what I thought would be more interesting is to actually think about the reaction. So in the reaction to make LaNiO2, we start with LaNiO3, and then we extract oxygen somehow to make LaNiO2. And a reasonable question is, well, what actually happens in the middle here? What's the mechanism of this reaction, and how can we think about controlling it? How does this actually work? It isn't magic. There's some chemistry going on in the middle here. And it's fair to say that not many people think about the mechanisms of solid state reactions. We think a lot about the mechanisms of molecular reactions, but what about the solid state? Well, you can get some indication as to how the mechanisms of these reactions work when they don't work quite as you would expect. And a good example of that is this reaction here. So this is the equivalent oxygen extraction reaction, but from what we call a double perovskite. Now we've got nickel and ruthenium as our transition metals, which adopt an ordered structure. And if I treat this with calcium hydride at 360 degrees C, I can make this compound, which has square planar nickel 1 and ruthenium 2 in its framework. And this material is quite interesting because it adopts a ferromagnetic state, a magnetically ordered state below 225 Kelvin. And it's a rather unusual example of a ferromagnet that's also insulating. And we can see why that occurs by understanding the exchange interactions between the d electrons on the transition metals nickel and ruthenium. Now, the interest here in this material is not just its physical properties, but the fact that its synthesis isn't straightforward. And this is a bit of a story of something that happened in my group, because we have a master's course, or actually our undergraduate course is only a master's course. And so at the end of the 4-year undergraduate program, you do a final year of research in research group. And a student joined my research group and managed to make LASR-NiRuO4 during their 9-month project. And everything looked relatively straightforward. But in 9 months, you can't finish all the characterization. So we had an incoming graduate student who was doing a PhD, or we call it a DPhil in Oxford. And I'm keeping them anonymous, so you can't see who's who. But the graduate student couldn't get this to work. That she followed the same procedure as the master's student, and it didn't work. And so, okay, well, try it again. And it still didn't work. And she and I have talked about this afterwards. And she said, you know, at the time, did you think it was me who couldn't do the synthesis properly? And I had to admit, yes, I did. But actually, she was very, very careful. And this is how we worked out what was going on. Because what is going on? Why doesn't the reaction work for her, but it does work for the master student? Well, the difference comes from how you make the starting material. And it turns out that the master student was in a rush. He just took the sample, that this material, LASR-NiRuO6, that you heat at 1100 degrees C, he just took it out of the furnace. Whereas the graduate student cooled it down slowly because she was worried about the disordering of the nickel and the ruthenium in this case. So she slow cooled the sample. And this is what changes the reactivity. And so if we do this carefully, we can see how it works. So what we're going to do is take a sample of LASR-NiRuO6, heat it up to 1100 degrees C. And then half of the sample we're going to cool down slowly at 4 degrees a minute down to room temperature. And the second sample, what we're going to do is we're going to take it out of the furnace and drop it into a crucible cooled by dry ice. So we're going to cool it as quickly as we possibly can. And then to these two separate samples, we're going to add calcium hydride, seal them in a glass tube, heat them for 4 periods of 48 hours at 360 degrees C. And what I'm showing you now are the X-ray diffraction patterns that come from that process. So the pattern on the top is the starting material. The pattern on the bottom is the final product, the reduced material. And then in the middle, we've got patterns from a slow cooled sample and a quench sample. And what we can see is that the quench sample has reacted much further than the slow cooled sample. The slow cooled is only converted about 25%, about a quarter of the material to the reduced phase. Whereas the quench sample has got 70%. And in fact, if we keep heating the quench sample for 2 more periods of 48 hours, we actually get the final reduced product. But if we keep heating the slow cooled sample, it doesn't react any further. And so a reasonable question is, well, what's going on? Why are the reactivities of the slow cooled and quenched samples different? We don't know yet, or I haven't explained that to you yet, but the first question on the way to that answer is to think about how do the quenched and slow cooled samples differ. Well, what we can do is take a synchrotron X-ray powder diffraction data from the 2 samples. So the diamond light source is about 20 miles away from Oxford, so we can make regular use of the synchrotron X-ray beams there. And if we take diffraction patterns of the slow cooled and quenched samples and we fit them to models, we find that they're identical. Their lattice parameters are identical to sort of 4 decimal places. The atomic positions are identical. We can chemically analyze them and show they've got the same amount of oxygen. They look principally identical. But if we look very carefully at the diffraction data, we can see that the diffraction peaks from the quenched sample, which I'm showing in red here, are very slightly broader than the slow cooled sample. And if we measure the width of the peaks as a function of the diffraction angle 2 theta, we can see clearly now that the quenched sample has broader diffraction peaks than the slow cooled sample. And what we can do from this evolution in the peak width as a function of 2 theta is we can extract the particle size and the strain from the 2 materials, because that's what leads to peak broadening in the diffraction pattern. And what we see is that the quenched sample compared to the slow cooled has smaller particles and a larger degree of lattice strain. And we're going to see that this is what leads to the change in reactivity. Now we can check this by, or at least we can check the particle size by doing an SEM measurement. So what we're doing is basically taking a picture of the particles, and then we can fit their sizes and show, yes, indeed, the quenched samples do have smaller particle sizes than the slow cooled. And the critical point is that the quenched sample doesn't really have any big particles, whereas the slow cooled sample has a number of particles greater than 400 nanometers. So why does quenching lead to a change in the particle size and strain? Why does quenching make the particle size smaller and increase lattice strain? Well, it turns out there's a structural transition in this system. Like many perovskites, we get tilting and twisting transitions in the framework to basically accommodate the A cations within the framework of corner-linked B cations. And so what we find is at room temperature, this tilting is out of phase. So it goes sort of left, right, left, right, left, right down the chains in the X and Y direction, but is in the same direction in the Z direction. And this is at room temperature. But at high temperature, basically it's alternating in left, right directions along the X, Y, and Z directions. And so we get a change from one to the other at about 400 degrees C. And what we find is if we slow cool samples to various temperatures and then quench them from those temperatures, we see that quenching from just above this transition temperature gives us the broadest peaks in the diffraction pattern. So that gives us the most strained and smallest particle size samples. So why does quenching do this? Well, what we see is that on cooling, we'll go from this phase, this R3 bar phase, to this P21 upon N monoclinic phase. And when we cool down, what we find is the symmetry in the system is broken locally. That's to say this tilt changes in a local way to make lots of small domains. However, if we look at the 2 symmetries of the unit cells, they're not related. They don't have what we call a group-subgroup relation. Or another way of thinking about it is that having 3 tilts that are out of phase along X, Y, and Z, we have no indication as to which direction we should put in phase. Should it be X or Y or Z? That gives me 3 choices. And then the in-phase tilt can either be clockwise or anti-clockwise. So my total number of choices is 6. So I can basically have 6 orientations of this tilt pattern relative to this one. And they're all equally likely. So what happens when you cool the system down is you get a sample with lots and lots of small domains, where each domain corresponds to one of the 6 possible orientations. Now, it turns out that the domain walls, so the joins between these different oriented domains, are very high energy. We don't want to have that reorientation. So the system will try and convert to a single domain of one orientation. However, that conversion process, that reorienting of the direction of the domain, is very expensive. It has a high activation barrier. And so we can only do that reorientation at temperatures close to the transition temperature. So if we slow cool a sample, we spend a long time in that temperature region and we can reorient a large number of the domains. But if we quench quickly, we don't spend any time at all in that domain growth region, and we get lots of small domains and high strain. So you might then ask, well, how does that lead to the difference in reactivity? Well, what we can think about now is a cartoon of the reaction. So here, this purple block is our sample of LASR-NiRuO6, our starting material. And what we're going to do is remove oxide ions from the system, but I have to remove them from the surface. I can't just teleport them out. And so what we're going to see is that the oxide ions leave the system from this surface to make an oxygen deficient region here. Now, what we see in our diffraction data is we actually don't see any intermediates between the fully oxidized O6 form and the reduced O4 form. And so what we have between these two compositions is a very sharp interface. We get a very sharp change in oxygen content at this position here. And if we look at the unit cell sizes of the reduced and oxidized forms, we can see in the AB plane, compared to the A over here, there's a difference. So we're about 0.1 angstroms different in the lattice parameters, but that's 0.1 angstroms out of 5. So you can see that's about a 2% lattice strain, and that's a very high lattice strain. And in fact, this lattice strain at the interface adds significantly to the activation energy of the reaction. So how does this affect the reactivity? Well, again, we can think about one of these reaction progress plots. And so what I'm again plotting out is the energy of our oxidized form and our reagent, and then our reduced form and our byproduct. And we need to get over this activation barrier in order to get the reaction to happen. And what we're saying is that by reducing the particle size, we make our particles more flexible. And so we can lower this activation barrier because we can mitigate against the strain that forms at the interface of the reduced and oxidized forms. And then when we add strain to the system, what we actually do is destabilize the starter material, and again, lowering the activation energy of the system. And so what I could do now is plot out the activation energy range of different samples. So we could start by thinking about if the intrinsic activation of the system, if we had a perfect infinite crystal. And then we could think about our slow cooled and quenched samples, where having a finite particle size and having a finite non-zero strain will then lower the activation energy of that reduction process. And what we're saying is that the slow cooled sample has lowered the activation energy less than the quenched sample has. So that if I perform my reaction at this energy here, you can see I can get all of the quenched sample to react, but only a small subset of the slow cooled sample to react. And so this is how the texture, the particle size and strain in a material can modify its reactivity in topochemical reactions. Now you might say, well, how is it that, why don't we just raise the reaction temperature to overcome this activation barrier? So rather than doing the reaction at this temperature here, why don't we do it at this temperature here? Well, generally that's what we would do. But in this system, we can't do that because we have a second reaction that we don't want to do. And this second reaction turns our product phase into the thermodynamic product of the simple binary oxides and the two metals. And what we need to worry about is the relative size of these two activation barriers. And what we find is the size of this second activation barrier fixes the maximum reaction temperature at 360 degrees C. If we go above that temperature, we'll start going over this barrier. So what I actually need to do is modify the size of this barrier in order to get the reaction to work. And that's what we did through quenching. Okay, so that's our first story. What I'm going to talk about in the second story now is another reaction we can do with metal hydrides and oxides, and that's turning our complex oxide into an oxyhydride material. And so what we're going to do is an anion exchange reaction where we take out oxygen and we replace it with hydride, so H-. And this is the first example of a transition metal oxyhydride. Now this reaction actually goes through an intermediate. You can think of this reaction actually first doing the anion extraction that we were just talking about to make this phase LaSrCOO 3.35. And then there's a second step in the reaction in which we replace 0.35 oxide ions and 0.35 vacancies for 0.7 hydride ions in a redox neutral anion exchange reaction. And what we'll see in the remainder of the talk is that sometimes we see this intermediate and sometimes we don't. But this hydride for oxide anion exchange is rather interesting and allows us to make rather exotic compounds. So we can make oxyhydrides now of our transition metal oxides that we start with. So here's this cobalt example. We've made a vanadium example, actually very many examples, where we can now think about including ruthenium and rhodium and iridium to make really exotic materials where now we have H- as our anion. So why do we care about that? Why is a hydride or an oxyhydride system interesting? Well, we can see that by focusing on this material here. So SrVO2H is an oxyhydride compound based on a perovskite. And so what I'm showing you here is the structure where the little red dots are oxygen and the big purple ones are hydride. And the material itself is an antiferromagnet at room temperature. We can see that by the neutron diffraction data here. This is a magnetic scattering peak, and actually from muon spin resonance, this muon resonant characterization method, these oscillations are characteristic of magnetic order. And actually what we see is the hydride ion is very good at coupling the magnetic moments on neighboring transition metals. But there's another interesting feature of the hydride ion. If we think about our starting compound in this reaction, this is SrVO3. This is a perovskite. It's a vanadium 4+ D1 case. So we see our d electron sits in our T2G pi symmetry orbital in a local configuration. When I exchange the oxide for hydride, my local coordination now becomes VO4H2. And I'm now a vanadium 3+, so I gained an electron. And this electron now sits in these pi symmetry orbitals. And the symmetry of this orbital is rather important because the hydride ion is a unique anion. It's the only anion of an atom that doesn't have any p orbitals. So it can't bond in a pi symmetry way. So we can't bond with these pi symmetry orbitals here, whereas you can see an oxygen 2p orbital can. And that leads to a rather interesting physical situation. So what we can do is we can calculate the DFT band structure of SrVO2H, and that's what I'm showing you here. And then we can integrate this back into a sort of a local configuration. So what I'm showing you here is the spin polarized density of states. So the left-hand side is spin up, the right-hand side is spin down, and we can see this filled band below the Fermi energy corresponds to filling the XZ and YZ orbitals with 2 electrons. And what we see is the Mott-Hubbard kind of interaction here leads to a band gap opening and insulating behavior. But what I can do is I can apply high pressure to this system and convert it to a metal. So if I put this in a diamond anvil cell and start applying greater and greater pressures, we can see what I'm plotting out here is the resistance against temperature, and we see the resistance comes down, excuse me, and the temperature dependence changes from semiconducting to metallic as we apply high pressure. So that at 60 GPa, what we've done to the structure is we've compressed the VHV direction by about 10% and the VOV direction by about 6%. We've really crushed the structure, and that closes the band gap and makes the system metallic. But the key point is that this large contraction in the C direction isn't what makes the system metallic. While the XZ and YZ orbitals are pointing at each other in that direction, this hydride ion sits with its s orbital between them and stops them mixing. And so even though there's a large contraction in this direction, this doesn't close the band gap. The band gap actually gets closed by the XY direction contracting, and that then broadens this XY band, which comes down to close the band gap. And as a consequence, what we find is that the band gap still exists in the C direction of our material. And so we end up with a metallic system that has very two-dimensional conductivity. The conductivity in the XY plane is much, much greater than in the Z direction. So that's a rather interesting system. But what we find is this high pressure analysis is really quite cumbersome. From a chemistry point of view, we wonder, could we get to the same metallic phase by doping SrVO2H? If I could remove some of these electrons here, could I put some holes into this band here and get a metallic system? And this is where, by trying to do this, this is where we learn quite a lot about the chemistry of the system. So you could think about A-site doping this, so replacing strontium, say, with a lower charged ion like potassium, but that's not possible. Instead, what we're going to do is we're going to replace some of the vanadium with a little bit of titanium. And so to make SrVO2H, what we actually do is start by making Sr2V2O7, which is a nice thermodynamically stable material. We then heat this under hydrogen at very high temperature to reduce vanadium 5 to vanadium 4 to make the perovskite, and then we do the calcium hydride reaction. So we could imagine now making a starting material at high temperature, which is now got titanium in and is likely to be slightly oxygen deficient. And we can then take this precursor under hydrogen to make the titanium substituted perovskite, and then treat that with calcium hydride to make the oxyhydride. And that sounds like a great plan, but it doesn't work. What we find in this final reduction step is that we don't get the mixed titanium vanadium oxyhydride. What I get is a vanadium oxyhydride and a titanium oxyhydride. What that shows us is these two perovskites don't actually mix, which is a surprise because the literature reports say that they do. But let's see what's going on a bit more closely. So if I basically try and make a 5% substituted version of SrVO3 by the route I said before, and I again take a synchrotron X-ray powder diffraction pattern of the product, what I can see is there's a second set of peaks here marked in red. So we've got a second cubic material, and we can look at the lattice parameters of the majority cubic material and the secondary cubic material, and then compare them to the lattice parameters of SrVO3 and SRTiO3, and we can see they're an exact match. And in fact, we've got 5% by mass SRTiO3, and we put in 5% titanium. And so what we can see is we haven't made a mixed phase compound at all. We've just made the two constituent single transition metal perovskites. And so when we reduce them, it's not surprising we get the two oxyhydrides. So how do we get around this? Well, another way we can make this material is through arc melting. So an arc melting furnace, basically, we strike an electric arc through an argon atmosphere. So we get an argon plasma, which is at a temperature of something around 3000 degrees C. So what that does is that melts our materials. And so we can make SrVO3 by melting strontium oxide and vanadium oxide together. So we think we could make this dope material by melting the vanadium and titanium together. And the key feature of this arc melting furnace is that it cools the samples very, very quickly. So we'll go from the melting point of the material to room temperature in maybe 10 or 15 seconds. So we're very rapidly quenching the material. So what's the product of this? Well, just to remind you, here's what the diffraction patterns look like for the ceramic synthesis of the vanadium titanium material. So this is where I get two phases, and you can see there are two big peaks here corresponding to the strontium vanadium oxide and strontium titanium oxide. If I take the same compositions and arc melt them, now you can see I get what looks like a single peak. Now it isn't quite. We do have two phases here, but you can see their lattice parameters are much more similar, and we have a significant majority phase, showing us that we are getting some titanium dissolved in the vanadium material. And so what we could do here is, you might think, well, I can make this a bit better by annealing, but if I anneal the material, it goes back to this two-phase example. And we can see why that is by thinking about what we're doing in the arc furnace. So in the arc furnace, we could take a ceramic product where I've got a mixture of strontium titanate and strontium vanadate. And when I melt them and quench them, I get like a frozen liquid where the titanium is randomly distributed through the solid. But if I anneal them, I'm allowing the system to have enough energy that the titanium vanadium can separate out again. So it shows that this titanium doped strontium vanadate is a metastable phase. But if I do this now for the 5% titanium doped material, so I arc melted and quenched it, I can get some titanium dissolved in the vanadium. We still have slightly two phases, but we do get some titanium doping. So what happens if I reduce this material? Well, what we find is something strange happens. So let me show you the progress. So what we're going to do is take SrVO3 calcium hydride to make SrVO2H calcium oxide and hydrogen, and now we're going to take the titanium doped version. So if I take the ceramic version, what I'm showing you here is the X-ray diffraction pattern of this reaction after 4 days. And what we see is we can identify these peaks as calcium hydride and calcium oxide. And then these two peaks that are like HKL indices, this is SrVO2H. And then we've got a vanadium titanium oxygen deficient phase. And as we proceed in time, that oxygen deficient phase goes away, and we end up with a single phase of SrVO2H. And if we look really carefully, there's our strontium titanium oxyhydride that came from the strontium titanium oxide that we had in our material. If I now do the same for the arc melted sample, after 4 days, again, I've got calcium hydride and calcium oxide. Here's my tetragonal SrVO2H doped with titanium. And then here's my oxygen deficient phase. And then I've got this unknown material here. And as we progress, that unknown material grows until it's the only product at the end. So we end up with a cubic material here rather than tetragonal SrVO2H. So what's this cubic material? Well, what we can do is actually analyze the product here and see, in fact, we've got 3 compounds or 3 phases in our sample. We've got a cubic phase that I'll show you is SrVTiO3-XHY. I've got a tetragonal phase, which is SrVTiO2H, and then I've got a little bit of vanadium from decomposition. And I can show, and we can just see the quality here, we can show this phase is the vanadium titanium oxyhydride by first doing a TGA analysis, so heating and oxygen and looking at the mass gain, and then we can do a titration for the vanadium oxidation state. And what we find is the majority product phase is now SrV.95, titanium 0.05, O1.5, H1.5. So we've gone from an O2H sample to an O1.5, H1.5 sample by just changing 5% of the vanadium for titanium. So the all vanadium gets this product, 5% exchange gets me that product. So what's going on? Why does 5% substitution make such a big difference to the reaction product? Well, the answer to that can be seen by answering a slightly different question, and this is to look at SrVO2H and its neighboring material SrCrO2H, because what we find is SrVO2H has ordered oxygen and hydrogen, whereas the chromium compound has disordered oxygen and hydrogen. And we can see why that happens, because in the vanadium case, these two d electrons sit in this XZ-YZ orbital, which is stabilized by having the 2 hydride ions trans to each other. But in the chromium case, the 2 hydride ions sit cis to each other, leading to a disordered material. And we can justify this on the basis that the 2 hydride ions are the strongest sigma donors in this system, and we have something called the trans influence, which tells us that 2 strong sigma donors shouldn't be trans to each other. So normally 2 hydrides would be cis unless we have this electronic stabilization. And this electronic stabilization means that the 2 hydride ions are trans, and then we can get oxide hydride order, and now I can shrink this distance because a hydride ion is more stable than an oxide ion. Okay, so that's the first bit of the answer. And then we can think about the reaction progress. So the reaction progress takes me from SrVO3 to SrVO2H, and then in principle SrVO1.5, H1.5, and finally strontium oxide and vanadium. And what we're saying in the all vanadium case is that barrier 2 is the largest barrier in the system. And so if I add enough energy to get over barrier 1, I can end up to make SrVO2H. But if I add enough energy to get over barrier 2, I've also got enough energy to get over barrier 3. So I can never stabilize SrVO 1.5, H 1.5, because basically SrVO2H is too stable. However, if I take the system now where I've substituted some of the titanium for vanadium, sorry, other way around, some of the vanadium for titanium, I've taken out a few of these electrons. What that does is destabilize this trans system. So I destabilize the O2H phase. And now barrier 2 changes to the size of barrier 4, which is now smaller than barrier 3. So I can get over this barrier and not that one. And so now I can make this intermediate phase. And you can see what that shows you is the electron count is changing the activation energy, and so it's changing the reaction pathway. Okay, so the very final story, I'm going to try and go quickly to get this in the time, is now to think about the different types of oxyhydride that we've seen. That I showed you this first oxyhydride that goes via an intermediate of a reduced oxide before a redox neutral anion exchange. But in the SrVO3 case, we'd never see an oxygen deficient intermediate. So can we understand what's going on here? Why are these two things different? And again, we can see this when reactions get complicated. And the system we're going to look at is actually this cobalt-ruthenium system. So this is the cobalt analog of the nickel-ruthenium system I talked about at the beginning. Because we're going to make this cobalt analog, LaSrCoRuO6, in just the same way as we did with the nickel one. And then we're going to quench it in just the same way as we did in the nickel sample. And then I'm going to mix this with calcium hydride in a sealed glass tube. And the product I get is this cobalt ruthenium oxyhydride phase here. It's a cubic material, and a combination of TGA and titration shows us that the overall formula is LaSrCoRu03.2 H1.9 with 0.9 vacancy. So very close to LaSrCoRu03H2. Okay. What I can also do is I can take lithium hydride with this material rather than calcium hydride, seal this in a tube, heat it to 320 degrees C, and now I'm showing you the neutron diffraction pattern. And what we see in the product of this reaction is I get two phases. A cubic one, a bit like this phase we saw before, and a tetragonal one. And if we look closely at the diffraction pattern, we end up with a series of extra peaks associated with this tetragonal phase, which we can see arise from oxide, hydride, and vacancy ordering. Unfortunately, we can't solve the additional structure for this, showing that it's partially ordered in the anion lattice. But what we see is the product of the reaction is something that looks a lot like LaSrCoRu03H2 and LaSrCoRu05H1. So we've got quite a large number of different phases here, so it's helpful to organize them on a phase diagram. And so what we have here is a slightly unconventional phase diagram of the anion lattice of this LaSrCoRu06 system. So in the bottom left-hand corner, we've got our starting material. And then as I move horizontally along the bottom of this phase diagram, what I'm doing is I'm taking oxide ions out and adding vacancies. And what this does is it decreases the transition metal oxidation state. We're doing a reduction in this direction. And then moving up the phase diagram, what I'm doing is a redox neutral exchange of an oxide ion and a vacancy for two hydride ions. So I turn O4 with two vacancies ultimately into O2H4. And what we can do is put our phases that we've made on the diagram. So here's the phase from the calcium reaction, and here are the two phases from the lithium reaction. We can see these two are quite similar. But what we find from doing those reactions is we don't see any vacant oxides. There are no phases that we've made down here, which is a bit surprising because what I can do is take the equivalent Ruddleston-Popper phase. So now we've got cobalt and ruthenium in the same oxidation states as the perovskite, but I've made a layered compound. And if I do the reaction here, what I find is I can make an oxyhydride, but I go via an identifiable intermediate, which is the reduced oxygen deficient phase. So I do an oxygen extraction reaction and then an anion exchange. So it kind of says that this oxygen deficient material is stable, but we don't seem to make it under the reactions with our perovskite. So can we make phases here? Can we make oxygen deficient materials here? Well, yes, we can if we start using reducing agents that don't contain hydrogen. So here's a good reducing agent that doesn't contain hydrogen. So this is zirconium. And we find if we treat this material with zirconium, we can make this oxygen deficient phase, LaSrCuRu-O5, which has a rather interesting and elaborate structure. And if we look at this structure, we see that our cobalt in blue comes in two different coordinations, a square planar version and an octahedral version, and then our ruthenium in purple sits in a 5-coordinate structure. And if we analyze this a bit more, we realize actually what we've done is we've got a cobalt 2 oxidation state on average, but actually this is disproportionated to cobalt 1 and cobalt 3, driven by the D8 square planar preference and the D6 low spin octahedral preference. So we have a rather unusual situation where we've disproportionated cobalt 2. And I think this is the first example of such a disproportionation, because the disproportionation of the heavier homologs below cobalt, so rhodium and iridium, are very standard. So we already made a compound which formally is rhodium 2, but is actually a 1,3 disproportionated product driven by the same reaction. Okay, so we can make an O5 phase, but can we make an O4 phase? Well, it turns out not with zirconium. The sample decomposes, but what we can do is if we treat this with lithium hydride, but now not in a sealed tube under flowing gas, I can make the O4 phase that we were trying to make. And we find that this is also a ferromagnet like the nickel example, but it has a higher ordering temperature, which is way above room temperature rather than below room temperature at 225. So now we can put these two reduced oxides on our phase diagram, so we can make the oxygen deficient phases. But there's an extra little bonus that we can add, which is when we analyze these materials, we often heat them on a TGA. And so if we, I've got myself out of phase. We'll come back to the TGA in a minute. So the point we're going to make here is we can only make these oxygen deficient phases without the hydrogen in if we keep the partial pressure of hydrogen low. And actually we can see these are intermediates in the reaction to make the oxyhydride, because what I can do is we can prepare a sample which hasn't completely done the reaction. So we can make a sample which is, say, 4.2 with hydride and with vacancies. And then if I seal that material in the presence of lithium hydride, it will then convert to the oxyhydride, showing that this is an intermediate. And what that means for the activation energies is, if we think about the case where we see the reduced oxide intermediates, what it shows is that the activation energy for sequential reactions is getting larger and larger and larger. And so if we add 400 degrees, we get over this barrier, but we stop here. Increase to 425, we get over that barrier, but stop here. And then increase to 450, we get over that barrier to make the final product. The implication in this sequence, because we don't see this intermediate if we have hydrogen present, is that this first barrier is larger than the second. So if I add enough energy to get over this first barrier, I can't stabilize this material here because I immediately go over the second one and make the oxyhydride. So we can understand why we get oxygen deficient intermediates or not by the relative size of these activation barriers. And as I was saying before, one bonus we can see is from a TGA measurement. So we often do a TGA measurement. So we heat a sample in a TGA, which is just a balance in a furnace. And if we heat these oxyhydrides under nitrogen gas here, which isn't pure nitrogen, we've got a tiny little bit of oxygen, what we see is they gain mass as they reoxidize. But we can then take the exhaust gas stream and put this through a mass spec. And what we're expecting to see is water from the hydride reaction with oxygen to make water. But we also see hydrogen gas made. So when we heat our system at 375 degrees C, this oxyhydride appears to be in equilibrium with an oxygen deficient phase where it gives off hydrogen, giving an idea that actually maybe we've got something that might be good for hydrogen activation catalysis. Okay, but the key take-home message is here we can form different phases on this phase diagram by controlling the temperature, but also the partial pressure of hydrogen. Okay, well, I think I'm just about out of time, but to summarize, I hope what I've shown you today is that we can start to control these topochemical reactions by thinking about their reaction pathway. So in the first story we saw I can control the activation energies in the system by the texture of the sample, so the particle size and the strain. We can control the pathway followed by the electron count. And we can also control the pathway by looking at the relative size of the different activation barriers for the different processes and adding different reagents, so either having hydrogen present or not. So it just remains for me to thank the people who've done the work, so a large number of graduate students and postdocs in my group over a long period of time, colleagues in chemistry here in Oxford and in physics who've helped with external measurements and calculations, and then a lot of external collaborators who help with a wide variety of different aspects of the work, and then external facilities where we can do synchrotron X-ray diffraction and neutron diffraction, and then a large group of funders. And finally, thank you very much for your attention, and I'll leave it there. Yeah, so in a sense, when we quench, yes, you can, exactly, yes. That, I mean, it's typical to do in cases, for example, where you have cation order or disorder. Yeah, exactly. Yeah, so the issue often with the arc melting is the rapid cooling. I mean, it gets very, very hot. So we think it can be of the order of 3,000 degrees C, so incredibly hot. But your sample is a liquid and it sits on a copper surface, which is being water cooled. So it has a very good thermal contact. And the samples are quite small, they're sort of about half a gram. And so they cool down very rapidly. And that's part of the arc melting advantage. Now we did with the first example with that nickel ruthenium oxide, we quenched that by taking a sample out of a furnace, and then it's in an aluminum crucible. What you do is you transfer the pellet to another aluminum crucible that's already been cooled by dry ice, so it's sort of at minus 30 degrees C, and that means you can cool down from 1100 degrees C to room temperature in maybe 20 or 30 seconds. So that rapid quenching means that we really shock the sample to get little domains which are highly strained and small particle sizes. But if you, the student who worked on this, Ella, who I think actually might be in the audience here, she spent a lot of time trying to find really good ways of quenching the material rapidly, because it really mattered. That quenching was a sort of a critical decision, or that quenching step is basically the difference between success and failure in the reduction reaction. And it really makes a big difference. Yeah, exactly. That it means you can trap in the high temperature state. So people use this for high pressure reactions as well, that you try and trap the high pressure form. So you heat it under high pressure and then you cool it under high pressure, and then you let the pressure off and hope that it stays in the high pressure form. So rapid quenching is a key way of making metastable materials. Yeah, absolutely. It, It kind of depends on your system. So you can try these topochemical reductions with non-oxide anions. However, it gets a bit harder. If you think about it, the driving force for the hydride reductions, if my talk is still working, no, it isn't, is that, oh yeah, I can do it this way, is that the byproducts that you make. Let me find an example. So if we think about, if I actually have written an equation somewhere, let me try and find it, that what we're interested in is, yeah, here we go. So if we think about this reaction here, it's actually driven by the formation of calcium oxide. That's the key feature. And so if you then switch to a chalcogen, so sulfur or selenium, what we need is the equivalent energy of calcium sulfide or calcium selenide to be high enough to get this reaction to work. And as the anions get bigger, the lattice energy gets smaller, so they don't necessarily work as well. So that's the first point. We do have examples where we try and extract fluoride, and we've managed to do that, and we can do that a little bit selectively, but the oxide comes out preferentially. And then thinking about the different reagents, well, what we find actually, if I can go all the way back to the beginning, and I've got the list, is that the different reagents behave in slightly different ways because, again, we need to think about the reaction that's happening on the side. So if we, you can't see my pointer, but if we think about the sodium hydride case, the reaction from sodium hydride to sodium hydroxide is actually topochemical itself. The structure of NaH and the structure of NaOH are very strongly related. So actually the barrier for the structural conversion from sodium hydride to sodium hydroxide is low. And so that's going to be reactive at low temperature. If we look at lithium hydride to lithium oxide, lithium hydride has the rock salt structure. Lithium oxide is anti-fluorite. And so the lithium lattice needs to change quite a lot to go from hydride to oxide. So you have to add the energy to get that conversion. And calcium hydride is even worse because you look at calcium hydride and you assume it has the fluorite structure. It doesn't. It has something called the strontium iodide structure, which is very different from the rock salt structure of calcium oxide. So again, the activation energy to get the calcium hydride to go to calcium oxide is a little bit higher. So if you want to do a really low temperature reaction, sodium hydride is your best bet. But if your oxide ions aren't very mobile, so you need to get above about 210 degrees C or so, sodium hydride is no good for you because it's sodium and hydrogen by then. So the next best then is either lithium hydride or calcium hydride. And there it depends because, again, you can see that the lattice enthalpy of calcium oxide is significantly greater than lithium oxide. So you get a better driving force, but the transformation of calcium hydride to calcium oxide has a higher activation energy. So again, you need to balance your system depending on the system we're actually trying to reduce. And the best thing to do is actually try all of them. It's not so difficult to try all of these reactions and just see which one works best. That's the challenge. So the intermediates are very difficult because we can make a parallel to molecular chemistry. So we think about molecular chemistry, we often have a sequence of different reactions. But what we don't mention in molecular chemistry, although not often, is that those reactions don't have a very high yield. So you can maybe only have an 80% conversion. But in a molecular system, that's fine because you can do a separation. You can see in the solid state, the separations are extremely difficult. And so when we go through a series of intermediates, and if I move forward to an example, what we find is isolating those intermediates is really challenging. So where are we? If we think about, where's this sequence? I've lost it now. If we think about this sequence here, so we go from the O8 to the O7 to the O6 to the O4H4. In that reaction process, you can't really isolate pure O7 or pure O6 because you always, if you're trying to make O7, you always get a bit of O8 and a bit of O6 present because that step is a bit of a blur. Likewise, the O6 is a bit of O7 and a bit of O4H2. We can make pure O6 by going through the zirconium route, by having no hydrogen present. But trying to make O7 by this route is quite difficult. You always get a mixture. So this intermediate, I guess the point is that the barrier um, between between O8 and O7 isn't so very different than the barrier from O7 to O6. So you always get, if you go over one, you always get a little bit going over the second one. So isolating the intermediates is quite difficult. Well, thank you very much. Sorry, I didn't hear that. Oh, thank you. Well, it's been nice to talk to you all this morning, or this afternoon in your case. Oh, good. Well, thank you very much. Bye for now.